So in this part of the video, we are going to talk about the existence theory for heat equation. Okay, existence theory for heat equation. Okay, if you remember, for heat equation up till now we want to talk about well posedness, right? And what did we derive? We derived that there is a unique solution. If omega is bounded, we have derived unique solution and the backward uniqueness too. But now we want to find the the heat equation solution, I mean existence. Yeah, so let's say you have given this equation ut minus Laplacian of u equals to 0. Okay, and this is, for now let's just assume this is in Rn cross, this is the time variable 0 infinity. So this is time, this is x. So this is your equation. Now what sort of functions can you think of which satisfies this equation? So for example, let's say u of xt equals to a constant, any constant k here. Okay, whatever is k is in R, let's say. Okay, k is in R, solves 1. So let's say that's your 1, solves 1. It's not very difficult to see, right? And of course, number 2, let's just assume that one dimensional heat equation, 1D heat equation given by ut minus ux x equals to 0. That's one dimensional heat equation, right? And what is the solution of this thing? U of xt, how does it look like? Any solution of one dimensional heat equation, it will look like this. So essentially it will look like u of xt is, see, I mean, I'm just showing you one way of doing this thing. I want a u such that whose one derivative with respect to t is the twice derivative with respect to x. So essentially, let's say u of t is t. Okay, u of xt, I'm starting out with t. So if you are taking ut here, it is basically 1. Okay, and minus this has to be uxx. So basically, you are looking for a u such that uxx is 1. Right, so uxx is 1 is essentially x square by 2, right? So you take one derivative is 2x and twice derivative is 2. So that is 1 and 1 minus. Okay, so this is one is a solution, right, of this. Let's say that's your 2 solves 2. Yeah, of course you can construct in such a way, you can of course construct a solution like this, right? Yes, which satisfy the 2-dimensional or n-dimensional heat equation. Yes, that is of course can be done, but we are interested in much more, right? If you remember from your Laplace equation, we derived something called a fundamental solution, which we used to solve, the Laplace equation, right? Which we used to solve the Laplace equation, the inhomogeneous Laplace equation. Yes, so we are also here also we are going to do exactly the same kind of thing. We are going to find something called a fundamental solution of heat equation. So fundamental solutions are, I mean, I do not want to give you the exact definition of fundamental solution. It's not very difficult. It's basically this thing equals to the Dirac delta. Okay, then any solution which satisfies that. But the thing is, I am not quite sure whether you guys know Dirac delta, because that is basically a distribution. Okay, so I'm going to skip all the, the jargons associated with fundamental solutions. So for now, it's a very, very special kind of solution. You can think of it like that. So what is the fundamental solution? Fundamental solution for heat equation. Okay, so you see, for Laplace equation we know what is the fundamental solution. I want to find it for a heat equation. Okay, fundamental solution for a heat equation. Okay, so so one small remark is this. See, remark, while finding fundamental solution, you remember for Laplacian we actually use the fact that it is rotational invariant, Laplace equation, and hence we look for radial solutions. Here no such thing can be done, because t, the variable t is a problem. I mean, t varies between 0 and infinity. That creates some problem. Okay, so what we are going to do is we are going to only look at some scaling factors. So one small remark, this I want you guys to check. So let u solves 1. Clear? If u solves 1, then if you scale this u such that u of lambda x lambda square of t, you do it like this for lambda in R, then this also solves 1. Is this clear? So if u solves 1, then u of lambda t, lambda square t for lambda in R also solves 1. Okay. Now this actually gives us some idea about what sort of so this you guys have to check it yourself. Okay, check it yourself. Not very difficult thing to do. I am absolutely certain that you guys can do it yourself. You just need some chain rule, application of chain rule. Okay, just do that. Now once you have this, so you see essentially what that says is we basically should look for solutions of the form u of xt as 1 by t power alpha, okay, some function v of x by t power beta. Clear? This is what, and alpha beta is in R. Okay, here v from Rn to R is the unknown. Okay, see here this says that if you scale the x variable as lambda x and t as lambda square t, so scaling is with respect to t it has to be lambda square, with respect to x it is just lambda. With this scaling what we can show is if you solve this equation, that scaling if you scale the u like that, then it also that particular function, this new function, that also satisfies the heat equation. So from here what you get is you are basically getting that there is a scaling going on between x and t, and we want to exploit that particular idea, and that is why we are just taking it like v of x by t to the power beta. Okay, so essentially if you think of it like this, it is basically x by root t, it should be, right? X by root t, x is lambda is 1. Okay, so here this should be square, right? I mean, if you want to scale it properly, so basically v of x by lambda root t should be there. Okay, but we are that should actually work here, yeah, but we are not doing that. We are just writing it as a arbitrary beta, and we want to find what beta is. Okay, now let's say this is 3. Now substituting 3 in 1 we get, okay, this we get as I'm just writing it down, yeah, alpha times t power minus alpha plus 1 v of y plus beta times t power minus alpha plus 1 y dot gradient of vy plus t power minus alpha plus 2 beta, okay, Laplacian of v of y equals to 0. Okay, how did we get this? I am just putting this thing in this equation. Okay, so basically you have this you write down what ut is, and after that write down what uxx is, and after that you just put it together. Okay, so this also you have to do it yourself. You have to try check it this part. Okay, it's very easy thing to do and not a problem. So here where y is defined by t to the power minus beta times x. Clear? So with this definition we are just writing it like this. Now you see here this beta is a problem. Why it is a problem? Because if 2 beta is 1, then all of this expression is basically the same, so I can throw out t to the power minus alpha plus 1, right? If 2 beta is 1, okay, then alpha beta is on our hands, yeah. If I am taking 2 beta to be 1, so this will become minus alpha plus 1, this is minus alpha plus 1, this is minus alpha plus 1. I can just throw it out, huh? If I throw it out, what will happen is the equation transform into alpha times v of y of course, plus half y dot gradient of v of y plus Laplacian of v is 0. Okay, this is what we are getting. And if you I want to simplify this further. Okay, so let us assume see again, v and all these things is on our hand, so we can assume whatever we want. Okay, of course it has to be, in line with whatever the equation says. Okay, so we can't just assume any arbitrary thing you want, but essentially what we are going to do is we are going to look for radial v. Yeah, so we are going to assume that v of y should look like some function w of mod y. Okay, for some w from r to r. So essentially I am looking for radial v which is radial. Okay, so if that is happening, again you can just take, this thing we calculated. If v of y is radial function of w, then Laplacian of v is w double prime plus n minus 1 by r w prime. This we did while we did Laplacian. Okay, so let's write it down. Of so plus half r w prime. Okay, because mod y is r here, so this is why r, and gradient of v is basically w prime, and this one Laplacian of v is w double prime plus n minus 1 by r w prime is 0. Okay, let me put it this way. This is for your Laplacian of v, this is for your half y gradient w, gradient of v. Okay, and this is of course alpha times v. Okay, see, gradient of v is radial, so gradient of v is just the derivative of v. I mean v is w of mod y, so that's why the derivative of w. Okay, so which is w prime. Y is r, right? Y is basically mod y, so that's your r, that's why I just replace it with r. Okay, so once you do all of these, what we can do is I can write this equation as r power n minus 1 w prime whole prime, okay, plus half r power n w prime whole prime. This is equals to 0. Okay, this is after setting alpha as n by 2. Okay, this is, see, once we now this alpha is also in our hand, so if I am choosing alpha to be n by 2, then that equation transform into this also. Please check it yourself. So there are 3 things. These are very easy things to check, so it's not a problem. And thus from here what we get? We get r power n minus 1 w prime plus half r power n w. This is equals to some constant c. C is some constant. Clear? Some constant. Now you see what happens as, I want to find that what happens to the limit of w as r tends to infinity. So we are assuming, see, this w is on our hand, so we are assuming that we are looking for a radial function such that limit r tends to infinity w equals to limit r tends to infinity w prime, which is equals to 0. Okay, this is what we are assuming. Why we are assuming this? Because this will actually give us c equals to 0. Clear? Okay, so if c equals to 0, therefore what will happen? See, what we are trying to do is we are going to try to find some solutions of that. Alpha beta is on our hand, so we chose beta in such a way that the equation becomes more easy. Now after that we chose w, which is a radial function, so essentially we chose v in such a way that it becomes a radial function, and we got this. Now I want to remove this c. Yeah, and of course alpha equals to n by 2, we are getting this thing, so I chose alpha also. Now I want to remove this c. To remove this c, I am assuming that the radial function which I am choosing will do this thing. Okay, that will give you c equals to 0. Now if c equals to 0, that what does that give me? That gives me w prime equals to minus half r w, right? From here I can just throw out r to the 1 n minus 1. Okay, so you understand, this is on our hands, we are manipulating, right? That is what we are doing, we are manipulating the solution. And therefore what do we have? If you want to solve this thing, we have basically w is some constant. I don't know what do I put, a b c, whatever I put everything. Let's say d exponential of minus r square by 4. Okay, let's just choose it. Write like d is some constant. Okay, d is some constant. So I hope you understand, this is all manipulation. We are manipulating our solution to look like this, that's all. Okay. So if you combine all of these, if you combine this w is what v, right? And if you combine all of these, then what do we conclude? We can conclude that the function which you are choosing, so our required function, let's say u of xt, how does it look like? It looks like some constant t, okay, by t to the power n by 2 exponential, this is exponential, minus mod x square by this e is exponential, okay, by 4t. Clear? So this is what we are going to get. Okay, so from here we are going to define the fundamental solution. Okay, so the function f of xt or phi of xt, let's say phi of xt, let's just call it phi of xt, which is given by 1 by 4 pi t whole power n by 2, okay, exponential minus mod x square by 4t, okay, and x is in Rn and t positive, okay, and 0 for x is in Rn and t negative is called the fundamental solution of heat equation. Okay, is called the fundamental solution of the heat equation. Okay, I hope this is clear to all of you. See, why it was happening is because we chose our u to be 1 by 2 to power alpha, right? Alpha we chose to be n by 2. Okay, so 1 by 2 with n by 2 only we are getting this solution. So alpha we chose it to be n by 2, that is why 1 by 2 to the power alpha, which is n by 2, and v is x by t to the power beta, right? So that is why v is w, so basically it is exponential of minus mod x square, r is mod x square by 4t, right? Because beta we just put the value of beta and this is what we are getting, and this is the fundamental solution of heat equation. Okay, so please remember this is a very important property, and so this this is a basis of all harmonic functions. Okay, sorry, not harmonic functions, this is a basis of many different analysis in harmonic theory, function theory. Okay, so let's write down some properties of this fundamental solution. So some properties of fundamental solution. Fundamental solutions. Okay, so number 1, for all xy in Rn and t positive, clear, fundamental solution of x minus y times t. Yeah, if you just write it like this is always positive. I hope this is fine. Exponential function is positive, this is a positive function, that is always positive. Okay, there is nothing to do here. Number 2, again for all xy in Rn and t positive. See, if you write this thing like delta t, so which is ut minus Laplacian of phi of x minus y times t. Yeah, can you guess what it is? This is going to be 0, right? Because fundamental solution, this actually solves the heat equation, so it has to be this. I hope you understand what is del t of phi. It is phi t. Okay? And for all x in Rn and t positive, okay, this is true. Integral over Rn, okay, phi of x minus y times t dy, this is going to be 1. Okay, why this is see, this is the relation which you want. So basically, why the integral of this fundamental solution has to be 1, just like in the case of heat equation, and just because of that we took this d to be 1 by 4 pi whole power n by 2. You understand? Yeah, that is the reason why we took this constant to be there. Okay, and number 4, the last property is for any delta positive, and for all x in Rn, clear, for all x in Rn, limit t tends to 0 plus, okay, and integral. So basically if you are looking at a fundamental solution above, outside in the exterior domain, okay, phi of x minus y times delta, t, okay, dy is 0, right? So these are the properties. So let me proof 1 and 2 are just like the easy one, huh? Let's prove the fourth property first, and then we are going to the third property. So the fourth property is limit t tends to 0 plus integral over the exterior domain, okay, this is greater than delta, x greater than delta. So essentially what it is saying is, if you are taking the fundamental solution of the heat equation, okay, dy outside the ball with radius delta, okay, so in the exterior domain, and as you push t towards 0, okay, as you push t towards 0, this is becoming 0, okay. How do you show that? So to show something like this, what we are going to do is, we are going to write this as limit t tends to 0 plus, this is some calculation, yes, let's write it like this, minus pi times n by 2, okay, minus n by 2, sorry, okay. So I'm just writing out what phi of t is, and after that I'm using a change of variable, yes. So I hope you guys can check this yourself, huh? This is not very difficult thing to do. So for mod z greater than 4 delta by 40, and that is why that there is 1 by 4 term is there, right? That's gone, because I'm just choosing my mod delta to be greater than delta by 4t, okay. This change of variable, under this change of variable, this turns out to be mod z square dz, clear, and that is becoming 0. Okay, so I'm just using a change of variable here, and writing phi to be mod z greater than delta by 2. On this domain, I'm just writing phi, which is exponential minus mod z square, okay. Once we does this constant will look like this, and you can show that as limit t tends to 0, this particular thing goes to 0, okay, because this is becoming smaller and smaller. You see, as t goes to 0, this particular thing for delta by 40 is going towards infinity. So basically you are taking mod z, which is greater than extremely big, yeah, mod z is extremely big. So and this integral, since it is summable, this has to be 0, okay. Now what about the third property? Third property is also a change of variable. So essentially it says that you see, essentially third property, you can write it like this, huh? There is nothing wrong in writing this thing, phi of t, let's say dx, yeah, phi of, you can take y, x minus y to be, we can just write it like this, right? Phi of xt. This is the fundamental solution. What these equations, the third equation says is integral over Rn, phi of xt or phi of x minus yt, whatever you want to write it. Yeah, that's not a problem. You can use a change of variable. So phi of xt dx, this is going to be 1, okay, for each time t positive. Now my question is, how do you calculate this thing? This is very easy. Let's write integral of Rn, phi of xt, okay, dx. This is 1 by 4 pi t whole power n by 2 integral over Rn exponential minus mod x square by 4t, okay, d of x, okay, and this is 1 by pi to power n by 2, okay, integral over Rn exponential minus mod z square dz. I hope this is fine, okay. Exactly the same thing which you did here, just a change of variable, okay. Once you have this, then this is 1 by pi to the power n by 2, okay. This you can write it as x1 square, x2 square, xn square exponential, that will break it up. So that will be the product of n equals to, I equals to I equals to 1 to n minus infinity to infinity exponential minus zi square dx, and that is going to be 1. Okay, sorry, this is dzi dzi, and that is going to be 1. Okay, so this is the properties of fundamental solution. Now in the next portion, next week, what we are going to do is we are going to use fundamental solution to find out the solution of the initial value problem of the heat equation. So with this we are going to end the lecture.